Under 9.4, we are told that we can use normal tables to find the mean and the standard deviation. We can find the mean and the standard deviation. And there are some 2 points to note, that if x is distributed normally between the mean and the variance, and the probability of x is greater than a is equals to alpha, where alpha is the probability, you write this statement as follows. This statement can be written as follows. Of course, we have x, which is an unfamiliar boundary. We need to bring in the z. How then do we write the probability of now our familiar z greater than, of course, our boundary is a, as per the question, a minus the mean over the standard deviation, which is giving us a probability of alpha. So when we have x distributed normally between the mean and the standard and the variance that way, and the probability of x is, when x is greater than a, is given by the alpha. Of course, when we introduce the z, we have to come up with the boundary in the question, a minus mu over the standard deviation. Sometimes neither the mean nor the standard deviation is given, in which case you will have to solve simultaneous equations. Of course, when you're finding the mean and the standard deviation, we cannot do that by simply forming a single equation. We have to form simultaneous equations, because you can already see that we have two unknowns, the mean and the standard deviation. And this one is going to be seen in example 5. So let's see what is in example 5. Having found that, let's see what is in example 5. In example 5, we are told the random variable x is distributed normally between the mean and the standard deviation of 3, or rather the variance of 9. Given that the probability of x when it is greater than 20 is equals to 0.2, we are told to find the mean. Find the mean. And of course, as much as we understand everything, when we have this statement, we must know that our unfamiliar boundary, which is not presented in the table on page 201 or even page 202, our unfamiliar boundary is 20. So if we want to introduce the z, like we've learned in the previous video or examples, we have to have 20 minus the mean all over 3, and this is what is giving us 0.2. That is the probability of 0.2. Diagrammatically, we are talking of something that looks like this. It is greater than, so the region is to the left, and the probability is 0.2, far less than half. So the value of whatever we are going to have as our z is going to be positive. Is going to be positive because this is now 0.2. What does that tell us? We should go to we should go to the percentage table because this looks a bit conspicuous. Then 0.2 might be provided in the percentage table, and yes, it is given. When we have the probability of 0.2, then the boundary, which is z, is 0.8416. And the reason why we have been able to go to the percentage table, because what is presented is z greater than. And we said z greater than, we can use the percentage tables directly. So if that one doesn't work, then we can go to 1 minus. Of course, we have our z, which is 0.8416. Whatever we are going to have this, that means 20 minus the mean over 3 is 0.8416. When we have that, 0.8416, then from this we can calculate the mean. And of course, the mean is going to be, if you cross multiply, then you're going to have 20 minus the mean is equals to 0.8416 times 3, whatever that is. Let's find it. 0.8416 times 3, which is 2.52, which this is the whole of this is 2.5248. Now, the mu which we are finding, of course, if it crosses over, becomes 20 minus 2.5248, and that one definitely is going to give us equals to, or rather the mean is 17.4752. 17.475.2, and that is it. But of the most important is just here that we did not have our z, so our unfamiliar boundary is 20, which has to be converted to z through the method that we learned in the previous example, and of course working throughout. But this diagram is also very important because it gives you a hint of where z lies. Right now we know our z is positive, and there it is. So our mean